Greetings everyone, this is Professor Roman. Let's continue the lecture series Transition to Advanced Mathematics. We have been discussing the fascinating subject of transfinite sets or infinite sets and their sizes. But we haven't yet defined the term finite and infinite, so let's do that now. A set A is finite if it's equipolant to one of the sets n sub k. N sub k, as you recall, is the set consisting of the natural numbers 1 through k, but n sub 0 is by definition the empty set. If A is not finite, we say it's infinite. And Theorem 1212 tells us that the natural numbers are not equipolant to any of these sets, n sub k, and so n is an infinite set, which of course comes as no surprise. I'm going to leave proof of this theorem to you. If A and B are equipolant sets, then A is finite if and only if B is finite. It's a rather obvious result, and the proof is only a line or two. This fact, this theorem, is key to many other results in set theory. Every infinite set A contains a subset that is equipolant to the natural numbers. Now, there is a very common proof of this theorem, and it's very short, and it goes like this. Since A is non-empty, we can take an element, A naught, from A. The singleton set A naught must be a proper subset of A, because if it was equal to A, then A would be finite, which is not the case. So we can grab another element, A1, from the set A, different from A naught. And then this doubleton set will also be a proper subset of A for the same reason. If this was equality, A would be finite again. Continuing in this way, we can extract an infinite sequence. This process can be continued indefinitely to produce an infinite sequence that is a subset of A. And so that is our set S that's equipolant to the natural numbers. Unfortunately, the phrase continuing in this manner, or something similar, is rather informal. And so this doesn't really constitute a formal proof. And you would be right if you were concerned about the validity of this proof. It seems rather obvious, but still you have learned by now from this course that we should not rely on informal proofs because they can sometimes be misleading. So here is a more formal version of the proof. And as you can see, it's a bit more detailed. And we're going to proceed by induction on n to prove the propositions P sub n. And P sub n states that the set A contains a strictly increasing sequence of subsets, S1 through Sn, along with a sequence of bijections. The bijection S1 sends F1 sends S1 to N1. And the last bijection here is between Sn and n sub n. Okay. But also, the function fk plus 1 is an extension of fk. In other words, fk plus 1 agrees with fk on the smaller domain sk for all k bigger than or equal to 1. Okay, so this is, if you remember back in chapter 10, when we discuss partially ordered sets, one of the examples was extensions of functions. That is a partial order on the set of partial functions. So this is, under that order, this is a strictly increasing sequence of bijections, where by increasing we mean extension. So we're going to proceed by induction on n. So first we need to establish the basis step P of 1. But since A is non-empty, we can take an element from A, call it A1, form this set, the singleton set A1, and so that will give us what we need here, which is just one set, because n is 1. And as to the bijection, S1 contains only one element, n sub 1 also contains only one element, the integer 1, and so we'll just send A1 to 1. That's obviously a bijection. So P1 is true. Now we assume that P of n is true, so we have this sequence of sets and we have this sequence of bijections. And what we need to do to show that Pn plus 1 is true is to find another set here, a subset of A, that would contain Sn, which shall be Sn plus 1. And we need to find another bijection, Fn plus 1, mapping Sn plus 1 to n sub n plus 1. Okay, I'll write that in here. We need this set and we need this function. Bijection. Okay. Well, as to the set Sn plus 1, we have this bijection Fn. It's this bijection right here. Okay. And this tells us that Sn is a proper subset of A, because if Sn were equal to A, then A would be equipolant to n sub n, and that would imply A is finite. It's the same argument we used twice before. Okay. And since Sn is a proper subset of A, we can grab another element, little a sub n plus 1, from the set capital A that's not in Sn, and throw that into Sn to get our set Sn plus 1. So Sn plus 1 has one additional element, An plus 1. As far as the bijection is concerned, all we have to do is extend the previous bijection by sending the new element An plus 1 to n plus 1. And that looks like this. So Fn plus 1 sends Sn plus 1 to n sub n plus 1. Fn plus 1 of x is the same as Fn of x for x in Sn, the smaller domain. It must be if it's going to be an extension of Fn. And An plus 1 gets sent to n plus 1. So we've got both our new set, top set, and our top bijection, so Pn plus 1 holds. And therefore Pn holds for all n, bigger than or equal to 1. Now we need to take the union of these sets S sub n, as n goes from 1 to infinity. And define a function f from s to n plus, which, if you recall, is the set of positive natural numbers. And what I want to do is define it this way. F of little s is Fn of little s, where n is at least 1, bigger than or equal to 1, is any integer for n for which little s is in S sub n. So let me put these both on the camera here. So what I'm saying is if you have a little s in capital S, you can take any set Sn that contains little s and use the corresponding bijection Fn. Take Fn of s, that will be f of s. Okay. Now, there's something at this point absolutely critical that we have to confirm, and that is that my attempt at defining the function little f is well defined, because it appears that the definition of little f depends on which n you choose, or more directly, which set Sn you choose. Okay. And we have to show that that's not the case, that no matter which set Sn you pick, as long as it contains little s, obviously, you're going to get the same value on this side here. So f of s is well defined. Okay. This is a very critical point. It's one of the really key ideas in this whole course. When you make a definition, you need to stop for a moment and say, is this well defined? Is there any ambiguity here? Am I making any choices, arbitrary choices? And if I am, does it matter which choice I make? If it does, you don't have a well-defined function or set or whatever you're defining. Okay. Well, if little s lies in two different sets, S sub m and S sub n, and we can assume m is less than n, then the point here is that Fn is an extension of Fm. Okay. When you look back at this sequence of extensions, each one is an extension of the previous one, therefore it's an extension of all the functions that came before it. So Fn is an extension of the previous, the earlier function Fm, and therefore the two functions agree on members of the smaller domain Sm. S is contained in that domain. So these two values agree, which means it didn't matter which set Sn or Sm you used to define the function f. Okay. So the choice of n or the choice of Sn, same thing, is immaterial. You get the same result regardless of your choice. And I strongly suggest that you think about that until you see the need to do this and the resolution in this case. So we do have a well-defined function f. And to see that f is injective, we could take two distinct elements, little s and little t of capital S. Both of these set elements belong to some set Sn. They may, at first, little s may belong to one Sn, little t to another, but those sets are nested. And so both elements will belong to the larger of the two sets. Okay. So both of them belong to, let's say, S sub n, But the function f sub n is injective. And so f of little s is equal by definition to fn of little s, and that is different from fn of little t because fn is injective, and this is equal to f of t. So f of s and f of t are different, and that makes f injective. Okay. To see that f is surjective, note that for any integer n bigger than or equal to 1, the surjectivity of fn, which maps Sn to n sub n, implies that there is an element little s in Sn that gets mapped to the integer n. So again, little s is in Sn, so f of s is fn of s, but in that case it's n. And so n has a pre-image under f. N was an arbitrary member of n plus, positive natural number, and so this is a surjection, and therefore a bijection. So S, which is the union of all the SNs, is in bijection to, or equipolant to, n plus, and that completes the proof. Well, you can see that to do a really proper formal job here required quite a bit more work than the informal proof. Now, I'm not saying there isn't a simpler formal proof. This was the idea that came to me when I realized that we wanted something more formal than the usual informal proof. So if you want to think about this, maybe you can come up with a shorter formal proof. Okay. Another way, by the way, to define f, which frankly just occurred to me, is these are functions, therefore they're binary relations, therefore we can take their union, and that is f. Now the union of functions in general is not a function, we discussed that before, but I'll leave it up to you to show that because of the special nature of these functions being a sequence of extensions, that just as we can take the union of the SNs, we can take the union of the FNs and we'll get a bijection. So I don't know if that's any shorter or not. It's a tad more elegant to use concepts that we've discussed, like the union of functions. Okay, so I'll leave that for you to think about. The key to the upcoming proof that includes the proof of this statement that we need is the following idea. Suppose we have a function f that maps a to b, and suppose it's injective or surjective or both. But we're not happy with the way that f maps the individual elements in the domain to the individual elements in the image. I've drawn a picture here. A1 is going to B1, A2 to B2, and so on. But we wish instead that maybe A1 went to B3 and A2 went to B1. So we'd like to change where the individual elements in the domain go. But we don't want to destroy injectivity or surjectivity. If the original function f had those properties, we want the new function to still have those properties. what do? Well, this is what we do. We decide instead where we want the elements of the domain to go, and we can arrange that by following F with a bijection of the image of F. And that's pictured here. So I've sent B1 to B3, and the reason I did that is because I want my new function to send A1 to B3 instead of sending it to B1. So once I decide I want A1 to go to B3, I know that my function g here, my bijection, has to send B1 to B3. I've sent B2 to B1, so now A2, under the composition, first goes to B2, then goes to B1. So I called this image scrambling. That's not a common term. I made that up, so you might not hear it elsewhere, but it seemed like a good idea. So the composition then looks like this, and it now sends A1 to B3, A2 to B1, A3 to B2, and A4 to B4. Okay. So that is the key idea. This is something we can always do. We can always change where elements in the domain go to in the image, and we can do it in such a way that if the original function is injective or surjective, the resulting new function is still injective or surjective. Okay? And this is a very useful idea. So here is the formal statement of the theorem. Let F be a function from A to B, an injection or a surjection or a bijection. And let G be a bijection on the image of F. Then the composite function, G circle F, is also either an injection if F was an injection, or a surjection if F was a surjection, and therefore also a bijection if F was a bijection. And the proof of this is just a consequence of two earlier theorems, so I'm going to leave that for you to write as formal proof. Look up theorem 11.9 and 11.12. It just says the composition of injections is an injection and the composition of surjections is a surjection, and so that takes care of the proof of this theorem. Now, the most important case of image scrambling for us will be just the swapping of two elements in the image. And here is the statement of what the theorem that I have in mind, and I called this image swapping for lack of a better term. Let F be a function from A to B, and let it be either an injection, a surjection, or a bijection. This is just a convenient way not to have to write three theorems, one for the injective case, one for the surjective case, and one for the bijective case. So it's shorthand, you might say. And let G be a bijection of the image of F. And suppose that we have two elements in the domain, A1 and A2, and A1 is sent to B1 under F, and A2 is sent to B2. Then the function G, again, must be a bijection on the image defined by swapping B1 and B2, but leaving everything else alone. So G of B1 is B2, and G of B2 is B1. G of X is X for all other elements. This is a bijection, and so the composition, which I called H, is also an injection or a surjection or a bijection. And it agrees with the original function F, except that the values on A1 and A2 are swapped. So H sends A1 not to B1 but to B2, and H sends A2 to B1. So that's a swap of what F did here. But H agrees with F everywhere else. Okay. So that's a special case of the image scrambling theorem, the previous one. Perhaps I should have called this a corollary. Actually, that's not a bad idea. The reason, of course, is that it doesn't need a formal, careful proof. It's just a matter of saying it's a special case of the previous theorem. Now we're in a position to prove this statement about equipolence among the sets n sub k, and a couple of other things, 3 other things that are going to be important for us as we proceed. So for the proof of this, notice I made this a bijection now. One direction is trivial. If k equals m, then of course these two sets are the same, therefore they're equipolant. It's the other direction, obviously, that requires the proof. So we can do that by induction on k to prove these propositions, P of k. And this says that for all m bigger than or equal to k, if nm is equipolant to nk, then m equals k. We don't need to worry about the case m less than k because there's a symmetry here. So if we have 2 of these, I'll call them n sets. If we have 2 of these n sets that are equipolant, nk equipolant to nm, then of course nm is equipolant to nk, so we can always arrange it so that k is less than or equal to m, or in other words, m is bigger than or equal to k, and so the proposition will apply. Okay. All right, so start with the basis step, k equals 0. In that case, we have nk equal to n0, which is the empty set. So P of 0 looks like this. For all m bigger than or equal to 0, nm equipolant to the empty set implies m equals 0. So in informal language, this is saying that the only n set equipolant to the empty set is the empty set. And that's pretty clear because a non-empty set cannot be equipolant to the empty set. And if that's not clear, if you are in the spirit of things here, you would say, well, I need a formal proof. I'm going to leave that for you to think about. Okay. So P of 0 holds. There is something to think about there, so I'm not saying there isn't. Okay. Now suppose that k is bigger than or equal to 1, and that P of k minus 1 is true. So that's for all m bigger than or equal to k minus 1, n sub m equipolant to n sub k minus 1 implies m equals k minus 1. We need to show then that P of k is true. So we can assume there's a bijection between nm and nk, and we have to show m equals k. Well, if this bijection happens to map m, which is the biggest element of n sub m, to k, the biggest element here, so if it happens, and we don't know this, but if it happens that f of m is k, then we can restrict f, restrict the domain, and in fact the codomain. We'll restrict the domain to n sub m minus 1. And that will turn, if the restriction is still bijective, because I reduced the codomain as well. So now the restriction takes n sub m minus 1 to n sub k minus 1. Okay. Just informally speaking, I lopped off the top elements. I started with this bijection, and if this bijection sends the top elements to each other, I lop them off, I get a new function with a reduced domain, reduced codomain, and it's still a bijection. But since m is bigger than or equal to k, m minus 1 is bigger than or equal to k minus 1, so the inductive hypothesis applies. In other words, we can apply the proposition pk minus 1. And it will tell us then that m minus 1 equals k minus 1. And of course, so m equals k, and that's what we want. So under this assumption that f takes the top element to the top element, we can do this. Now you see where image swapping comes in. What happens if f of m is not equal to k? Let's say f of m is some integer a, and f of b equals k. So m is being sent to something else other than k. It's being sent to a, but something is being sent to k because we have a bijection. Then we swap a and k. We do image swapping on a and k, and we get another bijection between the same two sets, and m and k, that agrees with f everywhere except m now goes to k, which is what we wanted in the first place, and we don't care what happens here. But b will go to a. Okay. And according to the properties of image swapping, since f was a bijection, h is also a bijection. And now we can apply the argument we just gave under the assumption that the original f sent top element to top element. H does do that, and so we can conclude that m equals k. So p of k minus 1 does imply p of k, and so p of k holds for all k bigger than or equal to 0. Okay. Now let's look at the proof of part 2. If S is a proper subset of Nm, then S is equivalent to an Nr for some r less than m. And this we will prove by induction on m bigger than or equal to 1. And these are the propositions that we're going to prove by induction. P of m now says that if S is a proper subset of Nm, then there exists an r less than m such that S is equivalent to Nr. If m is 1, then the only proper subset of N1, because this is a singleton set, is the empty set. So S would be the empty set, in other words, it would be N0. So we can take R equal to 0, and we will have S equivalent to NR. That's the basis step. Now we can assume that m is bigger than or equal to 2, and that P of m minus 1 is true. And take a proper subset of Nm. We need to show that S is equivalent to some Nr for r less than m. Well, if m does not belong to S, then S is actually a proper subset of n sub m minus 1. Why am I doing this? Well, I'm trying to use the inductive hypothesis, which is that P of m minus 1 is true, so I need a proper subset of n m minus 1. And so if this is the case, if M is not an S, then the inductive hypothesis does apply, and it guarantees that S is equipolant to an n sub r for r less than m minus 1, which then means, of course, r is less than m. And so P of m is true. So that case, namely m not in S, is proved this way. But what would you do if m is in S? Well, then we can take the set S prime to be S minus, throw out the element m. That is now a proper subset of n, m minus 1. And the inductive hypothesis will tell us there's a bijection, which I'll call F, from S prime, the smaller set, to nr for some r less than now m minus 1, because that's the exponent, the subscript here. All we have to do now is extend F to a function, which I'll call G, whose domain is now the full subset S, going into nr plus 1 by sending m, the restored element, to r plus 1, the additional element, top element here. Well, F was a bijection, and we've added a single element to the domain and the image and mapped that single element in the domain to that single element in the image, so F was bijective, G will also be bijective. And this will tell us that r plus 1 is less than m, and so P of m is true. Therefore, P of m is true for all m bigger than or equal to 1, and that proves part 2. Okay, now let's take a look at part 3 of the theorem. It says that if S is equipolant to nk and T is equipolant to nm, and S and T are disjoint, then the disjoint union of S and T is equipolant to nk plus m. This is the formal statement that says informally that if S has k elements and T has m elements and S and T are disjoint, then their union ought to have k plus m elements. So we are allowed to suppose that there's a bijection F from S to nk and a bijection G from T to nm, and S and T are disjoint. What we'd like to do is take the union of these two functions and get a function, bijection, that maps S union T to n sub k plus m. But that's not going to work, because when we take the union of these two, the image will be the union of nk and nm, and there's a lot of overlap there. If k is less than m, in fact, the union will just be nm. So we'll be way short of n sub k plus m. Just for example, F might send a little s to, say, 1, and G might send a little t to 1. So when we take the union, we're going to have two elements, s, a little s and a little t, both of which go to 1. And so we lose the injectivity, and therefore the bijectivity. The way to fix that problem is to make a change to, let's say, G. Either one would be fine, but let's say G, to get a new function, G prime, same domain, but now the union of the images of F and G prime is n sub k plus m. And of course, the new function also has to be a bijection. Well, that's not terribly difficult to do. All we have to do is shift the values of G so that instead of ranging from 1 to m, they range from k plus 1 to k plus m, because k plus 1 picks up where this set n sub k ends. The top element here is k. This will start at k plus 1. So G prime needs to send t bijectively onto this set, k plus 1 through k plus m. How do you do that? Just add k to all the values of G. And I'm going to leave it for you to show that this is also bijection. If G was a bijection, which it is, then G prime will be a bijection. Now the disjoint union of F and G prime sends S union T to NK union this set, and this, by design, that's why we did it this way, is N sub K plus M. And we had a theorem that if you have two functions that are, in this case, bijections, and their domains are disjoint and their images are disjoint, then their disjoint union is also a bijection. So that completes the proof of part 3. Finally, we have part 4 of this theorem. If k is bigger than m, there is no injective function f from the bigger set nk to the smaller set nm. Injections never reduce the size of sets because they're one-to-one. And so that's what we are trying to show formally here, at least for finite sets. So, if k is bigger than m, and if there was an injection f from nk, the bigger set, to the smaller set, we want a contradiction, then part 1 of the theorem tells us that f can't be surjective, because if it were also surjective, it would be a bijection, but k and m are distinct, so that's not possible. So the function f maps nk bijectively onto its image, which is a proper subset of n sub m. But then the image of f, which is equipolant to nk, is then, by part 2 of the theorem, equipolant to an nr, where r is less than m. And so part 1 tells us that k equals r, because these are equipolant, but r is less than m, and therefore k is less than m, and that contradicts the assumption that k is greater than m. So this type of function can never be injective. And that completes the proof. Okay. So let me just repeat what I said before. If you think about these 4 statements intuitively, they seem perfectly reasonable. But that's not what mathematics is about. That's a starting point. If it seems reasonable, the next step, and a critical step, is to try to find a formal proof so that you can convince the entire world that these are in fact true statements. Well, now that we've proven this previous result, we are in a position to give a formal definition of the cardinality of a finite set. The size or cardinality of a finite set A is the unique natural number k for which n is equipolant to n sub k. So the uniqueness was what we needed, and that is supplied by the previous theorem. Here are some basic properties of cardinality as it relates to finite sets. And as is the case with the previous theorem, the properties seem pretty clear. They're generally taken for granted. But now that we have a formal definition of finiteness, we can give formal proofs. So first of all, two finite sets A and B are equipolant if and only if they have the same cardinality. Proper subsets of a finite set are also finite and have smaller cardinality than the original set. So this is what it looks like in symbols. Cardinality of A is K. B is a proper subset of A. Implies cardinality of B equals R less than K. In particular, this tells us that a finite set is not equipolant to any of its proper subsets. Loosely speaking, a finite set doesn't have the same size as any of its proper subsets. That too seems quite obvious. But this is going to turn out to be rather an important statement, and we'll see that a little bit later. So that's why I highlighted it by setting it out in display format. And finally, if we have a family of n pairwise disjoint finite sets, so let's say the cardinality of Sk is equal to Ck, which is a natural number, then the cardinality of the union of these sets is the sum of the cardinalities. That's also something we take for granted. If you have a set of size 5 and a set of size 6 and they're disjoint, their union has size 11. For the proof of part 1, there exists n sets, nk and nj, such that A is equipolant to nk, B is equipolant to nj. And so theorem 1221 implies that A is equipolant to B if and only if nk is equipolant to nj, if and only if k equals j. That's the theorem part. And that's true if and only if cardinality of A equals cardinality of B. Okay. For part 2, we can assume that cardinality of A equals K and B is a proper subset. So there's a bijection, F from A to NK. If we restrict F to the proper subset B, we will have still an injection. Restrictions of injections are always injective. But we're going to lose surjectivity because this was originally surjective and we cut down on the domain. It's no longer going to be on to n sub k. So the image of the restricted function is a proper subset of n sub k, and so this previous theorem tells us that the image is equipolant to an n sub r, where r is less than k. And that means that B is equipolant to n sub r, so the cardinality of B is equal to r, which is less than k. And finally, for part 3, this looks like it's an inductive issue because this is for any natural number n, or any positive natural number n. I didn't say that explicitly, but when you don't say, and maybe I should have, that n is bigger than or equal to 1, you assume that that's n is arbitrary here. So we're going to use induction on the number n of sets in the family. When there's only one set, of course, the result is trivial because this is just the cardinality of S1 equals C1, which is certainly true. So we can assume that n is at least 2. For n equals 2, our previous theorem tells us that the cardinality of the disjoint union is the sum of the cardinalities. That was one of the parts of that major theorem. So we can assume that the result holds for families of fewer than n subsets and consider a family of size n. So the inductive hypothesis tells us that the cardinality of the union of S1 through Sn minus 1 is the sum of the cardinalities. And to kick this up by one set to S sub n, we can let S be this union. And then we can apply the inductive hypothesis a second time, because this union is the same as the union of S and S sub n. Now we only have two sets in our family, so the inductive hypothesis will apply. And so that is the size of S, or cardinality of S, plus the cardinality of Sn. This is the cardinality of S, and this is the cardinality of Sn. And that completes the proof.